Welcome and hello. This is a video lesson in HY-8, and what we're going to be talking about in this lesson is internal energy dissipators. So what that means is if you're in HY-8 and you click to edit your culvert crossing data and then come down here to energy dissipators, one of the three options in this top drop down here is design internal dissipator. This is the form that we're going to be talking about, the input data and the calculations. The purpose of energy dissipators in culverts is to reduce the velocity and energy of water exiting the culvert to prevent erosion in the downstream channel. Also in this drop-down, there's options for design external dissipator. That'll be a different video. And in the previous video, the previous lesson, we talked about estimating the scour hole geometry. That was lesson 10. This is lesson 11. Now, if you're using energy dissipators, let me go back to the input edit data. It's most likely going to be used where there's high flows and there's also a steep culverts. So for instance, right now I have a, 12% slope on my culvert. But if I changed it to a lower slope, such as, what would this be? About 1.2%, and I clicked on energy dissipator and then scroll down, it says this dissipator is not feasible. It's so out of range. But that wasn't the case earlier when I had the steeper slope. So let me go ahead and change that back to what is about a 12% slope. All right. Another requirement for the dissipators is the shape of the culvert. You need to be using either a box or circular culvert. So we're going to be looking at that in this video. But if I selected on elliptical, for example, and then clicked on energy dissipator, now we have a different error that says the dissipator is not feasible. Culvert is not a box or a circular shaped culvert. All right, so I'm going to go back to make it a box shaped culvert. Here's the shape, concrete box. I'm going to put in the dimensions of 6 feet wide, 5 feet tall. Click on energy dissipator. All right, from the top, we have some input data. The first thing we need to do is select the crossing and then select the culvert in that crossing and then select the flow rate. So this is the range of flow rates, which we defined earlier in our discharge data. I've currently defined the flow rates from 0 up to 1000 CFS. So that is the range that I'm seeing when I click on energy dissipator in this drop down right here. So that can change as well, but we'll just stick with 200 CFS for now. Below that, we have some culvert data. These are all just calculated values or input data, such as the size of the culvert, outlet depth, outlet velocity, fluid number, and so on. This is also for the 200 CFS flow. So if I changed it to 300 CFS flow, we have increased depths, velocity, and other parameters right here. There's 3 types of internal dissipators that we're going to be talking about, which is available to select from this drop-down type of dissipator. The first one is increased resistance. After that, we have tumbling flow. And then finally, the USBR type 9, which is for baffled aprons. All right, so let's get started with the first one. That's increased resistance. This method uses internal baffles, weirs, and roughened surfaces to increase the resistance to flow, dissipating energy gradually along the length of the culvert. So if I scroll down here, we can see the input data, which starts right here. I'm first going to bring up the user's manual. This is page 99, where it talks about internal energy dissipators, and it breaks it up into 2 sections. There's box culverts and circular. This is what we're looking at first, box culverts, despite the text saying circular here, where we have a few different parameters. So if I scroll down, we see here's the diagram, here's the flow from left to right, and then there's these distances or these dimensions that are shown. The length L right here, that is the length from the beginning of one roughness element to the beginning of the next roughness element. Roughness element being like a baffle or something on the side of the culvert. H right here, this dimension is the height of the roughness element, and then d sub I is the diameter of the roughness section. So that's not the entire diameter, but in this case it would be the entire diameter minus 2 times h. So let's go back to our input field. Now the data that it's looking for here is this roughness element height to hydraulic radius. So this is h divided by r sub I. I'm going to type in a number of 0.3, which is already there. It looks like the recommended range is 0.1 to 0.4. Not sure what the units of feet is doing here since it's length divided by length. And then the height of the roughened section right here, I'm going to go with 0.5 feet. Remember, my culvert itself is just 6 feet wide by 5 feet tall. So 0.5 right there. So I'm going to scroll down again. And then after that, we have our results. So we have results here, dissipator height, opening height, number of rows. Further down, we have element spacing. So we have the space to the first element is half of L, 2.5, and then the calculated value for L is 5 feet. So that's the distance between the baffles. And then the H value is zero point 0.5 feet. We put that in there. And then if we increase the flow rate up here, we should see some different numbers. So if I changed it to 900 CFS, that would affect some of our numbers further down. All right, I'm going to go ahead and switch it up to a circular cross section now. So instead of concrete box for the shape, I'll change it to circular. I'll say it's a 6-foot diameter. And then if I click on energy dissipator, design internal energy dissipator, increased resistance. Okay, that's good. Now we have a few different parameters to input. I'm going to bring up the user's manual once again. Here at the top are those 4 different terms. There's L divided by D, the ratio of roughness element spacing divided by the diameter of the culvert opening. The range is between 0.05 and 1.5. H over D, the ratio of the roughness element height divided by the diameter of the culvert opening, D sub I. And L divided by P, the ratio of the roughness length to inside perimeter ranging between 0 and 1. The D sub I is the last one. That's the diameter of the roughness section. We'll say that's the entire diameter, or maybe a little bit less. So if the diameter is 6 feet, let's go ahead and make that 5 feet. So we put that diameter right here, and then I tabbed off. It keeps moving me up here, so let me scroll back down. L over D ranges between 0.05 and 1.5. I'll just say it's 1. And then we have the roughness element height divided by the diameter. I'll go ahead and say 0.06, that's fine. And 0.5 is what I'll use for roughness length. That's halfway between 0 and 1. All right, so some of these parameters you got to play with and figure out what's best for your internal dissipator. But once I click off of that, the calculations should be made, and we see those down here. We see our results. We see the element spacing values. This time L is 5.89 feet. There's the space between the elements. That's the value of L. And then there's the total length of 29.4 feet. All right, that was the increased resistance type of internal energy dissipator. The next type we're going to talk about is tumbling flow. So I'm going to go ahead and select that here. Let's check out what the user's manual shows us. This is on page 101. Here we go. Tumbling flow. This is what it looks like. This type of dissipator is suitable for steep terrain where drop is unavoidable. Internal steps promote turbulent energy loss by transitioning flow from supercritical to subcritical multiple times along the barrel length. So you can see the parameters right here. L, again, is the distance between the roughness elements. And then we have a few different height elements, H1, 2, and 3. So you can see that in this diagram right here, which is the height of the roughness element. H2 is the height of splash shield on the ceiling, H2 right here. And then H3 is the culvert rise. So for a 6-foot diameter or a 6-foot tall box culvert, that would be 6 feet, that H3 value. So if we go back to our data input, here is the diameter of the enlarged culvert. Okay, so I'm on circular now. I'll just leave that at 10. It gives me the range up here. And a lot of these energy dissipator input data, it gives you the range for acceptable values. And then further down, we have the results. And then let me go ahead and switch that back to box culvert. That's what I wanted to do here. So shape, concrete box. We'll say it's 6 feet wide, 5 feet tall for the rise, energy dissipator, and then tumbling flow. And then I'm seeing some of those calculations once again. The last type of internal energy dissipator is the USBR Type 9. Baffled apron is what it's called. Let me go ahead and bring up the user's manual and scroll down to that image right here. So we have to specify the height of the dissipator and the width of the chute. Right here it says the partial block height is between 1/3 and 2/3 of H, which is the height of the dissipator. And if you zoom in, you can read some of the equations here. But anyway, whether you're using a circular or a rectangular shaped culvert barrel, then the input data is shown here. There's the approach slope, which says it's 0.5%. The vertical drop, I'm just going to leave these numbers here at 10 feet. The baffled apron, I'm going to go ahead and say that's between 25 and 50. So we'll say 25. And then the baffled apron width of 6 feet. So once all those numbers are put in, go ahead and scroll down. Look at your results one more time. We have the channel depth, velocity, slope, apron velocity and apron drop. And then there's dimensions for the baffle apron as well as the baffle block. These little baffle blocks here are shown with the height, width, and spacing all in units of feet. So that would give you an idea of what the size and dimensions are of this particular baffled apron type dissipator. This dissipator type is best for high velocity flows, especially for dam outlets. This method uses baffle blocks in a standardized layout to reduce velocity through turbulent mixing and hydraulic jumps. All right, well, that was it for this lesson where we talked about internal energy dissipators. Specifically, we talked about the increased resistance, tumbling flow, and USBR Type 9 fold apron.